Have I looked at you? If I put the right clothes on you, you could be a drug dealer. I can assure you. With that smile and with that sales pitch, you could probably do just about anything. 40 years from now, when you're some billionaire, remember this moment. Of course, hopefully you won't be a drug dealer billionaire, but you think so? In 40 years? Okay, we can stop talking about drug dealing. Okay, let's talk about something else. What else would you like to do? Nothing. Yeah. You could become a fashion consultant. Yeah. Yeah. To teenagers, maybe adolescents, that kind of thing. You're giving me a headache. Okay. So what we're going to do is we're going to take and convert the differential equation that we just non-dimensionalized into the BltzTrn form. And again, this probably shouldn't be called the BltzTrn transform. It should be called the BltzTrn substitution. This is a trick. Neon warning sign. This is a trick. It only works for this problem. Okay? So why cover it? Because it has some of the most horrendous algebra you've ever seen. And I guarantee your eyes are going to roll back in your head and they're going to look at your childhood and say, I hope there's something good on the other end of this. Okay? Did they? Okay. So as we finish tonight, we will end up with the exponential integral solution, and we will begin talking about how to approximate the exponential integral into a logarithm. Okay? None of you guys are old enough. Eric's massaging his forehead, which means his probably brain's starting to ooze out of his ears. Do you guys remember the Taco Bell commercials with the Chihuahua? Yeah. They took them off the air because it was insensitive, but man, that was hysterical. You guys remember those? Remember the one where he walked through somebody's house while Jeopardy was playing? And they said, what is a number the same as the base? No? You don't remember that? And the Chihuahua looks at the TV and goes, what is a logarithm? And there were two old people watching TV that just kind of like that. So there, we're going to be talking about the logarithmic approximation. Okay, that one fell flat. They can't all be funny. Thank you, Mr. Joker, for helping my career there. Okay, I know this is terrible. I should write it out in PowerPoint or something, but, this is the real deal. This is the real world. All right, so we start here. We make the substitution of RD, make the substitution of PD, make the substitution of TD. And you notice that I start carrying these little constants for different unit systems. No problem. The initial condition is the uniform initial pressure. The inner boundary condition is the -1 for our rate condition. The outer boundary condition is PD as RD approaches infinity is equal to 0. Okay, so the first thing we do is we go back and we write out our equation and we say, what are we going to do with this? This is a compact form. Okay, we say, I want to convert time and radius into an alternate variable. I'm going to use a power law relationship. I'm going to use a variable of substitution that has an A, a B, and a C. Now there's another derivation that's in the notes that explains why A, B, and C have to be what? 1/4 plus 2 and -1. And if you want to study that, that's in the notes, in the original notes. So the Boltzmann transform variable for this problem is RD squared over 4TD. We are going to take epsilon D is equal to RD squared over 4TD. We're going to substitute it into equation 8. And about 10 minutes from now, we're going to have a solution for this problem. Why does this only work for this case? You remember the case where we did the gas diffusivity equation? I made you do all that work, and then I showed you how to break it. Okay, I'm going to make you do all the work, and then I'm going to show you how to break it. Okay. Where's the algebra coming from, Cam? I've got to use the chain rule to convert all of those derivatives from d by dx, d by drd or d by dtd into d by d epsilon d. Okay, so all of that stuff on the right hand side is the chain rule substituting in there. Are you okay? I'm starting to lose you, buddy. Okay. Okay. So when we start at the top, we're going to take a look. We're going to separate it out. And the first thing we're going to do again is anything that is a partial derivative, we're going to apply the chain rule. So d epsilon dx, dp d epsilon. That's how we're going to write it out. So d epsilon drd, d by d epsilon d, d epsilon drd, dp d d epsilon d, 1 over rd, d epsilon drd, 1 over pd d epsilon drd, or sorry, dpd d epsilon d, d epsilon d dtd dpd d epsilon d. Okay, you ready to just jump to the end? I knew you would be. Here's, after all the algebra is figured out, so we need to know what is the second derivative of pd with respect to epsilon d. Well, that's fixed. We need to know what the second, d epsilon d drd squared is. We need to know what this term, d epsilon d, the second derivative of d epsilon d drd squared. We need to know again the first derivative, d epsilon d drd. We need to know it's squared again. We need to know what d epsilon d dtd is. Okay, so what is d epsilon d dtd? It's simply minus 1 over td epsilon d. What is the d epsilon d drd? It is 2 over rd multiplied by epsilon d. What is the second derivative? So take the derivative of this. That's d squared epsilon d drd squared. That is 2 over rd squared d epsilon d. Okay, so we need to substitute this, and this into here. That's the next step. And what's going to happen is it all reduces to this. Okay, so I made you do all that work to get to this differential equation. This is a second order ordinary differential equation that's set equal to 0. Now, I know I left it in terms of partials, but it is only in terms of epsilon d, so it's technically an ordinary differential equation now. Sorry about that, math ladies. All right, so the first thing we're going to do is we're going to say, let's look at the initial condition. The initial condition says that as time is equal to 0, what's going to happen? That condition says what? That PD is going to be 0. Okay? And remember, what is epsilon d? RD squared over 4TD, right? So if TD is 0, what's going to happen? As TD approaches 0, epsilon d approaches infinity, okay? So this condition says that as epsilon d approaches infinity, PD is equal to 0. What's the second condition, the outer boundary condition, class? It says that as RD approaches infinity, this is equal to 0. And obviously, epsilon d over 4TD, as that happens, or sorry, RD squared over 4TD is equal to epsilon. So as RD approaches infinity, epsilon d approaches infinity. So equation 17 and equation 18 are identical. What does that tell you? We have successfully combined two conditions into one. This is the only time it works. This only works for what? Uniform initial pressure and infinite acting outer boundary. Okay, that's the only time this works. All right. So now what we have to do is decide how we want to solve this, and we also have to set up the constant rate inner boundary condition, which is RD dPd drd at RD equals 1 is equal to minus 1, and or as RD equals 0 if you want to use the line source solution. So we have to come back and change this to dPd d epsilon d, and so when we do that, then RD is approaching 0, and epsilon, we need to know d epsilon d drd, which we learned from before is 2 over RD epsilon d, and then of course we have to say that RD is approaching 0 and epsilon d is approaching 0. So when we do that, that condition becomes -1, except that there's a 2 over here. So this condition, the previous inner boundary condition, becomes now epsilon d dpd d epsilon d as epsilon d approaches 0 is equal to -1/2. Now, how do you solve equation 16? How do you solve a second order ordinary differential equation? You integrate it twice. Okay. So the first thing we're going to do is introduce a variable substitution. We're going to say that v as in violin is the derivative dpd d epsilon d. And when we do that, we substitute it, and obviously the derivative of that is dv d epsilon d. And then we have 1 over epsilon d, and we have v. And we set that equal to 0. So we rearrange, and what is the integral of this expression? So we have 1 over v dv minus d epsilon d minus 1 over epsilon d d epsilon d. What's that going to be, class? This is going to be a logarithm. What's the integral of d epsilon d? Minus epsilon d. What is the integral of minus 1 over epsilon d d epsilon d? It's the log of epsilon d. And then we have to have a constant of integration, beta. So we solve this, and when we work out all the algebra, v is equal to some alpha term, which is the exponential of beta, over epsilon d exp of minus epsilon d. Does anybody see this, Joker? Do you see where this is going? We have a 1 over epsilon d exp of minus epsilon d. That looks like the kernel of the exponential integral, right? Okay. So now we have to solve for the constant of integration, and when we do that, we have to remember the definition. So we take the limit as epsilon d approaches 0 of this expression, epsilon d d epsilon d, dpd d epsilon d, pardon me, which is just that exponential, and that gives us 1/2. So alpha is equal to minus 1/2. So this is our final form, equation 25. dpd d epsilon d is equal to minus 1 over 2 epsilon d exp of minus epsilon d, and that's equation 25. Now we integrate that, okay? And what do we integrate it over? Well, we're integrating PD from 0 to its value of PD, so it's a definite integral on the left-hand side. And then we have minus 1/2 epsilon d, and then epsilon d equals infinity, because that's the definition of epsilon d at time equals 0, and because this is PD at time equals 0. And so what does that integral look like? Well, it looks exactly like this if we switch the limits, and we have 1/2, and then we have infinity, and then we have epsilon d equals rd squared over 4td, 1 over y e to the minus y dy, and we work out all of that. That's just the exponential integral e1. Now, a lot of people call this ei, and the SPE nomenclature calls this ei. Why don't I call it ei? Do you remember? What happens when you use ei is it's minus ei of minus x is e1 of x. So you end up carrying around an extra minus sign for no reason, okay? So that's why I always work in e1. e1 is the first exponential integral, and it again is defined as minus ei of minus x. For some reason, SPE prefers to have minus ei of minus x everywhere, which really confuses the hell out of me and other people. So the final answer is here, okay? And that's your exponential integral solution. Now we are going to rederive this tomorrow night using the Laplace transform, okay? Are we going to get the same answer? Yes. It's the same mathematical problem. How often in life do you get exactly the same form from two different solution approaches? Not that often, but in this case, because the BltzTrn transform has some unique capability here, this is what we get. Now I need to ask a question as a reminder. Did everyone remember the special functions lecture that Alex did for you? It was the one that was not recorded on the screen but was recorded on the box. Do you guys remember that? Do you remember a lecture where he talked about the exponential integral? Do you remember a lecture where he talked about K0, K1, I0, I1. We're going to start doing a lot of K0, K1, I0, I1. So be prepared for tomorrow night. You may want to read the notes ahead of time. Okay. What could you do with this problem? What could you do with this problem? Let's go all the way back to the first. In this case, could you have, just as in a theoretical sense, could you have a permeability distribution as a function of radius for this problem? Mr. Liu says no. Anybody else? I didn't say it was practical. I'm just asking, could you use this Boltzmann transform concept to solve a problem that you couldn't solve by other means for exactly, precisely this initial condition and this inner boundary condition? Yes, no, maybe. Can you give me an example? You know, if they ever take this away from me, I'm going to be lost. Sorry? You'll have to work out the definition, but you can define a permeability as a function of position and time, okay? And you can substitute it, all the algebra is back here. Here's the setup. You'll have to define your Boltzmann transform. You have to define these, and you can set it up as a dimensionless permeability system, and then you substitute it in like this, and you'll do the Boltzmann transform with permeability as a function of radius, and it does work. It's this is a non-linear solution, so you cannot use this approach for buildups, but for drawdowns you can. So this is just one other case that I was able to. I'm looking for the plot. Sorry. Yeah. So you have a profile. We took this from some data that was in the literature, and we fitted it with those permeability profiles. And then what happens is when you use those permeability profiles to generate dimensionless pressure derivatives, this is what you get. So just sort of FYI. Where's the little box that makes it bigger? Yeah, there you go. Oops. I didn't just do that, did I? Does anybody recall what this looks like? Sorry? It looks sort of like a radial composite system. So you can imagine that as you have a permeability distribution that's propagating out, it will look sort of like a radial composite system. There's an issue with how this thing propagates, so it doesn't look exactly like that. But at any rate, I just thought I'd throw that in. You don't have to, don't worry. That's not on the test. So, okay. So that is one possible use of the Boltzmann transform. Could you try to solve the gas case with the Boltzmann transform, class? Mr. Liu says no. But that wouldn't help you. The Boltzmann transform wouldn't help you with that. you're correct that that's a function of time and radius, but moreover, it's a function of pressure, and it's a cyclical argument. Okay. Just checking. Just want to make sure you guys are thinking about this. Is there something else that could be propagating? I mean, the only thing I could think of was permeability. Conceivably, you could have a water bank. And actually, I tried to have a student solve the moving bank problem, and we were not successful. But the way we set this problem up with a permeability that propagates, that did work. But I think it would be extremely difficult to have a bank of alternate diffusivity moving. It would be a really difficult problem to model and maybe not be solvable at all. Again, I just wanted to show you this as an example of how the Boltzmann transform could be used. And the point about that is that don't forget, you know, even though this is painful, and I know you don't want to be here and study this sort of stuff, but there could be an application to a problem that you're interested in using classical methods. Now, you know, I didn't talk much about this in the past, but I'll say that Dr. Ayala at Penn State and another fella in Brazil and we all had the same concept of how to solve the gas problem analytically. And it was, I say the same concept, we were all directionally working in the same direction. The guy in Brazil did it a little bit differently, but my student that was working on it really was having a hard time with it. And I was, you know, sort of leading them slowly. And about that time, Dr. Ayala started publishing his results, and you could hear me banging my head on the table. But, you know, it's still a classical approach to a very old problem that has value now. And just be aware that there may be some problem that you're trying to solve that this could apply to. And, you know, just because I've been obsessed with unconventionals doesn't mean that the classical solutions aren't worth studying. They are, because there may be something in this that helps us. Recently, there's been an enormous amount of work done on so-called anomalous diffusion problems. Anomalous diffusions are where you have to use fractional derivatives to represent the properties of the system and stuff like that. To me, it's way overkill, but you know, it's still worth doing. Who's a big anomalous diffusion problem person? Eric, Dr. Ozcan, and then his previous advisor and another student, previous student of theirs, is a competitor working in that area. And I've got a student working on something that looks at an alternate for anomalous diffusion. And there was some work done in like 2012 or so that was actually funded by the National Academy of Science here in the U.S., which was trying to solve the gas problem for the shale system with a sort of, it wasn't really anomalous diffusion, but it was a specialized approach. So even then, classical approaches can be used. So if you see a particular characteristic flow regime, there's probably some underlying reason why that's happening. If it's anomalous diffusion, that's fine. I mean, those of you who went to the papers this week and you saw the paper that was difficult, which I don't know if any of you did, you know, there was two contrasting views on that. That's fine. That's okay, you know. And it doesn't mean that someone's right and someone's wrong. But right now, we're talking about trying to solve these kinds of problems with one form or another. You know, what's the proof? Somebody tell me, how do you prove definitively that it's not a fractal reservoir system and that it is not anomalous diffusion, or that it's something else? You can't. Everything we do in this business is by induction. We have a pressure and a rate and some time, you know, and we're trying to infer all of this from that. The equation we derived tonight has been the classical solution in hydrology and in petroleum engineering since when? Something in the 20s was the first time it showed up, the so-called Tice solution, right? Same equation. Is it absolutely valid? Do we know? My feeling is that on a macro scale, Fluid flow behavior has certain characteristics. And by macro, I mean like the size of this room or the size of this building. Macro is supposed to be something you can hold in your hand, but using Darcy's law to define it, I think we're probably okay. Just out of curiosity, what's the practical implications of all this? So in 2011, when I went to a forum on unconventionals, there was a gentleman from a super major who said, "Oh, you American cowboys, you don't know what you're doing. We're company X," and it's not Exxon. Sorry, I didn't mean to say that, but we're company X, and we're going to figure this out, and we're going to own this area. Well, they had a very difficult start, let's just say. Yes, there's still a lot of questions in petrophysics. Yes, there's still a lot of questions in fluid flow. But at $100 a barrel, you had companies that were whipping company X's behind on deploying wells and getting. If you can pay off a well in 6 months, and math ladies, this is your moment of entrepreneurial clarity. If you can pay off a well in 6 months, the rest of its life is profit. That's pretty good. And that at $100 a barrel, you were paying off wells in 6 months to a year. Now, some wells are probably being paid off in a year. Most are probably 2 years. But are you willing to wait on your investment for that long? Yeah. And have we figured out what's causing this? Do we know any more now than we knew in 2011? Or do we apply things differently now than we did in 2011? Not really. So what's the message? Why should we be doing all this? Gabe? Mr. Liu? Mr. Bake? How much of the oil and gas are we getting out of these systems? Definitely less than 10% of the oil. And probably on the order of 20, 25% of the gas. That doesn't bother you. There's a lot left. How are we going to get it? We have to understand the fundamentals to go after it. How much money was spent on thermal EOR in this country? How much money was spent on chemical EOR? When I was your age, people were contemplating injecting pure oxygen into the reservoir. There was a company called Oxinject or something like that. And I was your age, and I went to their booth, and they had like a table with a broken leg at ATCE. And they said, we're going to inject pure oxygen. And I was like, are you insane? Do you know what pure oxygen will do? It'll flash probably before it hits the reservoir, or the second it hits anything hydrocarbon, the temperature and everything else. You're going to have an instantaneous. Do you know what the word for combustion is in French? No? Nobody wants to guess? Gabe? It's oxidation. They refuse to call it combustion. But the second that it hits, what's going to happen? Poof! You don't need a starter. You don't need a flame source. Pure oxygen hitting hydrocarbons at X 100 degrees Fahrenheit, it's a done deal. Ladies, what about injecting nitrogen? What about the rest of you who've been studying all this? Would you inject nitrogen? Will nitrogen make oil swell like carbon dioxide? Yes. Well, what's the miscibility pressure of nitrogen? So we're back to carbon dioxide. And if you have a free source of carbon dioxide, it might work. What's the problem with capturing carbon dioxide at a power plant? It ain't free. Somebody invented a system to extract carbon dioxide from the air in Switzerland. And they estimate that it will extract 1,000 tons a year. 1,000 tons a year. How much does that power plant put out over there? I would say several orders of magnitude more than 1,000 tons a year. It's another good question. Right now, it looks like we're going to store carbon by having more people. So we'll just have to think about that. And that is not a social commentary. It's just a statement. It's a joke, okay? I told you guys the best single thing I ever saw in storing carbon was to inject it into oyster beds and cause them to grow. But then we're going to have an oyster bed surplus, you know, or something like that. The worst possible thing you can do is probably, you know, try to sequester it and hope for the best. But some really good friends of mine, that's their job. So I'm going to ask for a mulligan.